Hello, everyone. This is Mike Traskos with Lectromec, and welcome to our first webinar. This one is on lessons learned from EWIS evaluations of aging aircraft. Thank you, everyone, for coming to this. I know it's in the middle of the day, and I appreciate you taking the time for this. Obviously, today we'll be going over getting information on database decisions for aircraft EWIS sustainment. This is going to be the first in our webinar series, and I'm hoping that we will be doing more of these over the rest of the year. For those that have been receiving our newsletters and have been reading our articles, I hope that those topics will be of interest, as we'll be covering those periodically through webinars through the rest of the year. We will be recording this webinar, and we will also have the webinar available in a couple weeks after this broadcast. So we'll be sure to send out information on that once we get to that point. So as I said, I'm Mike Traskos. I'm the president of Lectromec. I'm an EWIS DER. I'm the chairman of the SAE Wire System Installation Committee, and I've been doing this for about 14 years. And for those that have been reading articles, I'm sure you know that this is a topic that I care a great deal about, and hopefully it'll be of interest to you, and hopefully fill in some of the gaps about and some of the questions you have about EWIS evaluations. So here's what we'll go over. We'll talk about some of the costs of EWIS, some of the background behind EWIS sustainment and evaluation, data collection, maintenance, and some of the things that go along with the service life assessment for EWIS, and kind of some of the lessons that we've learned along this path. As a starting point, obviously I need to talk a little bit about Lectromec. Our business is a certification for aerospace wire systems and components. We've been doing this for more than 30 years, since 1984, and we work with everyone from component manufacturers to end of life for the operators and so forth. We were one of the key contributors to the Air Force's standardization of EWIS risk assessment, and I'm proud to say I was a part of that. And we are an ISO 17025 accredited lab. So that's who we are as a company, and really EWIS is what we care most about. For those looking to kind of get a grasp on the cost of EWIS, we go pretty far to try to figure out where, try to find numbers associated with costs. Some of the best stuff we can find came from the US Navy, when they identified that they spend about $75 million annually on wire-related issues and troubleshooting and maintenance. Now, if you take that same ratio for spending per aircraft, then the US Air Force spends about $120 million annually on EWIS. When I presented these numbers to the Air Force maintenance managers group a couple weeks ago, none of them said that we were crazy saying such a thing, so it seems as though we're within the good ballpark on that. Now, how much time is actually spent on EWIS maintenance? Best estimation we can come up with and have found is about 3 to 10%. I know that's a fairly wide range, but it's the best estimate we have at this point. Now, maybe that doesn't cover everything, because when we look at the amount of money and time that certainly the DoD puts into identifying no-fault founds and all the equipment behind that, back in 2005, they spent on average $1 billion or $2 billion annually. So obviously that's probably increased over the last 13 years, and without a doubt there's some portion of that that's probably EWIS issues that are causing no-fault founds throughout their fleet. Now, from a commercial perspective, the top 5 US commercial airlines experience an EWIS emergency abort, takeoff, or diversion once every 6 days. If you want more information about that, we have a white paper that's on our homepage that kind of describes how we came up with that figure. But certainly it's a good thing that it's so few, but obviously it's impacting commercial airlines on a regular basis. So the how and why of EWIS service life extension, and why this is an important thing, and why there's even a handbook behind this. Back in 2010, the Air Force identified that they had a glaring omission in what was identified, a glaring omission in their service life extension, because there was no guidance on the assessment of EWIS. They had procedures for structures, hydraulic lines, and various other aircraft systems and components, but really nothing for EWIS. And what really happened was there was a 30-year-old fleet. It was wired with polyamide or Kapton, if you prefer. And they were going through their life extension, and they wanted to know, do we need to look at the EWIS? Is that really something that needs to be evaluated? So the fleet went to the folks over at the Air Force Research Lab and asked, well, is this something that you recommend we look at? Well, the Air Force Research Lab guys, these guys who have been there for decades and certainly had seen the changes in the importance of EWIS and know certainly the degradation of EWIS, and they were part of the TWA 800 incident investigation, and certainly a lot of investigations in the Air Force for crash investigations. And the Air Force Research Lab guy said, well, yeah, it's a 30-year-old aircraft, it's polyamide, you probably should take a look at it. So Fleet Office got that and said, well, if we look through our incident history, we don't have a Class A mishap or catastrophic event that involved EWIS. So that Fleet Office went down the path of saying, no, we really won't look at that. Now that went back and forth, and basically what they found was that both sides were arguing over anecdotal evidence and had no real data. And after that back and forth for a while, the research lab came to a point that they really just wanted to create a methodical, defined process that will allow for what you would do with EWIS. And the outcome of this was MIL Handbook 525. If you go to Lectromec's website, we have several articles about this, and you can certainly find the publication on the DLA.mil website. This publication is derived from industry, regulatory, and military sources, and really provides a comprehensive process for EWIS assessment of aging platforms. One of the benefits that we had putting together this handbook was that this was put together about 2012, 2013, and that gave us a couple years after the FAA had published their documents, their advisory circulars and regulations that went around the EWIS. And this allowed some time to digest that information and kind of see how it works in practice. And then we looked at that from a aged platform perspective and got a lot of input from industry and those within the military to really come up with a good process that could be applied to a lot of fleets. Now, this is a handbook, and it's really designed as guidance and something that could be tailored to meet the specific needs of a fleet. So for those that haven't gone through the handbook, it really comes down to a 7-task process. The first task is data collection and impact analysis. Really, you're doing a system safety analysis on EWIS. You're gathering the data about it, identifying the functional, physical characteristics, doing collocation analyses, and really system level analyses. And here you're looking at the failure severity. At task 2 through task 4, you're trying to gather information about failure probability. In task 2, it's data mining, looking through maintenance data and identify, really look through and see what information you can glean from EWIS repairs and the reports that are there. In task 3, this is aircraft inspection, on-aircraft evaluation of EWIS. Task 4, this is where a lot more information about failure probability comes in. EWIS component degradation analysis and remaining life forecasts. In task 5 of the MIL Handbook 525 is the risk assessment. This is where you take the information from task 1 and task 4 through task 4 and bring it together to create a comprehensive EWIS risk assessment. And if you have enough information with regard to component degradation, then it's possible to predict future EWIS risk. And we'll talk about that when we get to that section. Task 6 is an action plan. Obviously, everything here is designed to actually support the fleet. Support I know I say fleet, this is whether commercial or military. It's really applicable to both. But you're looking to develop a plan to really improve the maintainability and the reliability of the aircraft. Last task is task 7. This is where you're progressively coming back and evaluating the condition of the aircraft and looking what needs to be done to maintain airworthiness. And the rest of this presentation will kind of line up with each of these tasks because it's a logical way to do it. And a lot of the lessons we've learned fall into each of these buckets. So we'll go through that one by one. But as a starting point, it's something that I feel I typically need to reemphasize. The EWIS risk is, well, risk at its basic level is the combination of failure probability and failure severity. For EWIS, that failure severity is really a combination of both the physical, the physical and functional failures, and they should be quantified. And that's something that if you're familiar with the EWIS regulations for the commercial side, that's your tree breakdown that you see in the AC that's associated with 25.1709. So we'll start with fiscal separation. And like any good Lectromec presentation, we have a video of an arcing event. But obviously the question we often get when we talk with non-EWIS people is, why do we look for physical separation? Well, first, the failure consequences of arcing are very high, and a single separation distance cannot be used for the entire EWIS. As an example here, we have a 2-gauge wire and a 16-gauge wire harness. Think about the circuit protection that's attached to a 2-gauge wire and what's attached to a 16-gauge wire. Clearly, there's more energy available in a 2-gauge wire harness, and certainly what energy is available there can certainly do damage to nearby components. So you can't assume that there is a single separation distance. Over here on the right, we have a high-speed video of a 115-volt 3-phase power arcing event, and what you see, hopefully you can see this through the webinar here and on the screen, is down here we have a 1-inch aluminum tube, and it's separated from this arcing wire harness by 1 inch. You see that there's a lot of material that's bouncing off the tube. You see that this illuminated area, though, that's the arc plume, and that temperature can vary quite a bit, can be as high as 5,000 degrees Celsius. So even if there's no direct electrical arcing between that wire harness and the tube, that arc plume makes it's possible for that arc plume to heat up the tube sufficiently to a point where that metal will weaken and there will be a rupture. This is a pressurized hydraulic line or fuel line, then this turns into a flamethrower. There are multiple incidents which have had that failure scenario, and this is just a short little animation showing that. So in task 1, we're looking to get physical failure impact, and that means trying to identify the separation between wire harnesses and critical aircraft components, fuel, hydraulic lines, etc. A lot of this information can come from drawings and just evaluating the 3D models if they exist. But for some of those areas which are high density or have had multiple changes, it's recommended that you go in and you do a on-aircraft inspection. Now, you can't do this with every section within the aircraft, and that's some of the things that we certainly learned, that you need to evaluate where you need to really think about where you're looking and when you're looking. And this overall process is going to, the size and scope of it will vary based upon obviously the number of people available, the amount of resources, and certainly what's viewed as the importance of the program. And so to adjust the total number of areas to look at or the systems to be evaluated, you can focus on just the category 1 systems, or your systems that are related to catastrophic impacts. To limit the number of harnesses to evaluate, you can focus just on the larger power wires, things that are larger than 18 gauge. It's not ideal, but it helps to focus on some of those areas where the physical impact is very high. Certainly high density areas with wiring and pressurized lines, those are important, and without a doubt the co-location with anything fuel system related. Now, how much information you can get out from this Task 1 EWIS evaluation is dependent upon how deep you want to go into the EWIS. At the high level, a system level loss where you're really just looking at the criticality, your depth of analysis is very limited. But if you can start to bring in some of the circuit diagram information about how it's routed through the aircraft, well, then you can start doing the failure modes and effects analysis, start doing some co-location analysis, and depending upon the amount of data available, start to do some arc fault hazard analysis. Lastly, if you really follow everything that's recommended in terms of data gathering from the Mill Handbook 525, you can do a lot of analysis and really get a lot of information about the condition of the aircraft wiring system. Now, this seems like a lot of information. This seems like a lot of data to churn through, but there are software tools available to help expedite EWIS assessment. One of the tools that Lectromec offers, or we work with and we use ourselves and we built, is the EWIS Risk Assessment Tool, or what we use for short, the EWIS RAT. If you want more information about that, we certainly have that on our website. So going over to Task 2, gathering data. Task 2 is focused on gathering maintenance data. Looking in and trying to find out what is the condition of the wiring based on what the failure reports are. Anytime, of course, you look at old maintenance data, you need to be reminded, of course, that historical data trends do not identify potential issues with aging. Certainly, you can do Weibull analyses and try to predict future performance, but that requires a lot more knowledge about the components, the material performance, and so forth. So the best recommendation I can provide in past experience, don't over predict what the maintenance data will provide. And certainly one of the challenges is going through this maintenance data, and I'm sure several of the people on this webinar have done so. Maintenance data, trying to pull out the EWIS information, is a time-consuming process. Simply doing a keyword search never really works. It gets you a very small set of the data. And certainly other things that impact it are no fault founds and improperly assigned maintenance codes. It makes it a difficult process. There are data tools that are available. We've been working on it ourselves for this last year, and you can get, if you've used the right tools and you know how to use them properly, you can get a lot of information. You can actually identify better than 80% of EWIS failures out pulling them from maintenance data. Now, if you believe you can pull out 80% of the EWIS related events and even chain them back to the original error report, such as we need to replace this box, and that's happened multiple times. If you can actually chain that back, you can really start to see and assign costs with EWIS related events. Task 3, inspections. So the level of visual inspection is really dictated by two factors: the level of access to the area and the EWIS protection. Now, we know that there's not much space available on aircraft, and there's a lot of stuff crammed into those small spaces. So to get the most out of an EWIS inspection, it really needs to be aligned with heavy maintenance actions. I know that That's sometimes a challenge because there's so much work going on, and any sort of inspection or analysis may impact that. But this is really the best time, and scheduling should be done during this time. It provides a lot more information and provides a lot more access to the aircraft. It's certainly areas of the aircraft that are not really available through most of its service history or service life. Of course, as you see here in this figure, aircraft protected with additional harness protection are very difficult to evaluate. It's very hard to see any sort of degradation or damage to wires that are behind NOMEX or heat shrink tubing. And so in those cases, really the best thing you can do is look for the small sections that are exposed. See what you can glean from, is there any sort of overheating damage? Is there overwork? Can you see any sort of cracks in the top coat or the top layer of insulation? It requires an attention to detail, and it's really when you're looking at a section like this, it requires a lot of patience, because if you're not focusing on trying to get that information, you can get very little from looking at an area like this. Certainly, you hope that you don't look at sections of the aircraft that are as dirty as this, but it's going to happen. If the wiring is obstructed, it should be cleaned and inspected. If otherwise, what are you doing in the area? Information needs to be gathered as part of the overall process. And if you get in here and you actually do the cleaning and you look at the samples or the wiring and the components and the connectors and everything here, you get a lot more information. Anytime there's heat damage, it needs to be noted. That heat damage can impact the conductor, the insulation, any shielding. And what you really need to keep in mind here is that if you're looking at a zone and you start to see some regular damage along the wire harness, see if it's maybe just an old clamp. We've actually had cases where clients have tried to figure out why there's been heat damage in a certain section of their wire harness, and it turns out it was just really transfer from a clamp. So knowing what you're looking at is really something that we would recommend, and one of the lessons we've learned. Also, depending upon the size of the aircraft, you really can't look at every zone, and unless you have a large team devoted to going through it. To help reduce the total number of zones to be evaluated on the aircraft, use the information from Task 1 and Task 2 to help focus the effort. If Task 1 identifies that there is a section of the aircraft that has a high risk or high severity, a failure severity, focus on that area. If the Task 2 data analysis shows that there's another area that is low priority and never has shown a failure, that should be ignored, or have a very limited inspection. So Task 4, remember, from Task 2 to Task 3, we're looking to try to get information about the health and the probability of failure within the EWIS. Task 4 looks at predicting the performance of the aging EWIS. And so for the EWIS components, the evaluation should be done in such a way to help with planning future maintenance actions. If you're looking at the components, really there's two ways to evaluate their performance. There's a kind of a limited requalification, which looks at the condition of the component and compares it against the original performance. So if you take a wire, you'd say, oh, here's the insulation resistance when it was new, and here's where it is when it's at this point in its service life. Now this is great. It provides, doesn't really you don't need in-depth knowledge of the component. You don't need to know how the component materials degrade over time. And it does provide some information about the component performance. The problem with this approach, though, is that it cannot provide data cannot provide data for future projections. If all you know is where it is and where it was, but you don't know how it will progress over time, well, then you're limited to the here and now. Another way to look at components is to perform a degradation assessment. Obviously, the positive here is that you can use this information to predict future performance and reliability. The results can be correlated with performance criteria. Now, one of the problems that certainly we've seen is that a lot of these degradation assessments don't really correlate to or are not part of qualification tests. So as an example here, we've done a lot of research on a lot of EWIS components, and I've picked right here just the cross-link ETFE. Cross-link ETFE progressively degrades over time due to exposure, certainly due to heat. And so if you were to take a component, take some wire when it's new and it performed here, and then after 30 years, it lost 30% of its performance, would you say that's still good to be on the aircraft? Well, we did the research and said, okay, well, 30% is still good. You still can work with it, and from a maintenance perspective, it won't randomly fail due to maintenance actions or random shock. But if you go another 20 or 30%, then it's at that point where you start to see cracks, and it really becomes susceptible to failure due to any shock. And so we say, okay, if you're here after 30 years, after another 10 years, your wire will now be at this condition, but you're looking for your service life to be extended another 15, well, then you'd want to consider potentially replacing the wiring from that zone. And what that allows for, and this is something that can be applied to a wide variety of EWIS components. If you use this, then you can say, okay, if we can plan 5, 10, 15 years out, and we know how the degradation will perform, how the degradation will evolve of our EWIS components, then we can start getting things in place. We can start saying, okay, if we need to replace it in 10 years, we need to start getting funding at year 5. We can start getting those components ready in year 7, and then when that aircraft comes in for service in year 9, everything is ready, we can make the hot swap, and it's good to go. So this is something that we've been working on for decades, and we cover a wide variety of EWIS component degradation with our research. Now, things that can impact its performance. Predicting performance is really dependent upon knowing where stuff comes from, knowing some of the history, because like a lot of things that we do in this world, if you put garbage in, you get garbage out. So it's necessary to know what is the condition or what's the history of that component. As an example, we had a client a short time ago, actually I've had a couple clients over the last decade, who have been doing some rewiring on their aircraft. They basically took the wire, dumped it all into a box, and at some point they said, hey, we should probably figure out what the condition of this wiring was to see if we can help the other aircraft in this fleet. So they sent it to us, we did the evaluation, and the results really didn't match our expectations. And so we wanted to find out more and asked the client, well, can you tell us how old these wires are, and do you know exactly where they came from? And unfortunately, they could not. All of the identification for those wires have been stripped. It was just thrown into a box of wires that come from roughly 4 different areas within the aircraft. If you give us garbage, if you're really going into this effort and you don't track everything, then you're going to get garbage out. And this kind of leads into the second point here. Not all components are the same, and they certainly will not age the same on the aircraft. I think everyone here would probably expect a component in the wheel well to degrade much more rapidly than one inside the cockpit. So there's really no reason why those samples should be grouped together and in a single evaluation. They should be considered separate, and each of those zones should be evaluated separately. Now, if you take all the maintenance zones on the aircraft, you probably can group them in about somewhere between 5 to 12 environmental zones. And it's important to know the proper boundaries and don't over group zones. it's always advantageous to say, oh, well, we will reduce the number of zones. We'll say a couple are very similar, and we'll put them together. But by doing that, you start to either overestimate or be a little bit too conservative in what the condition is. And it really again, not all the components are the same, and not all environmental conditions are the same and have the same impact. Last point with regard to task 4, aircraft can be grouped together by similar service histories and age. This obviously can help to reduce the number of aircraft that need to be evaluated. I mean, if you have a fleet and you look at just a couple aircraft, look at the ones that are potentially different, have different service histories, and that can certainly provide a good scope and currently actually a good view into the condition across the entire fleet. Task 4, last item that on this one is if you look at the condition, you actually can predict forward, which is one of the things that I think Lectromec does a great job at. You can start to predict, you can start to look at when you need to get things replaced. And I kind of touched on this a couple slides ago, and I got ahead of myself, but from an actual visual perspective, you can see here we have a best and worst case condition. And for this EWIS component group, we would say that the 50% mark is where the performance degrades to such a level that the reliability is no longer there, where you're going to start seeing age-related failures. So in the best case for our zone 3, we say that would be around year 12, and for our worst case around year 9. And as I mentioned earlier, this allows for prediction and a means to get ahead of maintenance actions before it starts impacting aircraft reliability. Task 5, this is where everything comes together. This is where you start to bring together this is where you do bring together the severity of failure, which was identified in task 1, and the probability of failure information that was brought in from task 2 through task 4. And the idea here is that if you can get an aircraft and you can break down the zones to identify which areas have the highest risk of EWIS failure and highest risk from the EWIS, you can then focus your maintenance to the areas that have really the best impact. If you can reduce the maintenance in certain areas, then obviously you can put that time into the more critical areas and potentially save time and money. Of course, if the entire aircraft is in terrible condition, which is something we've never seen happen, then it may be beneficial to increase maintenance actions until performance has improved. So this is a small figure that as a little figure that we put together to kind of help to show how risk can evolve and what actions can be taken to improve aircraft EWIS reliability. So in this example, it's fairly straightforward. You have it's a standard risk matrix. And along the top here, we have severity of failure. And along the vertical, we have the probability of failure. As numbers go up, obviously the severity and probability also increases. In this group here, we have 5 different wire harnesses, and we say, okay, we've evaluated the wire harnesses, we evaluated the probability and severity of failure, and we've assigned some numerical value to that. It's really a qualitative assessment at this point. So if we were to evolve that from that point in its current condition, 10 years forward, we see that the probability of failure evolves for each of the zones, for each of the wire harnesses. And here we have a wire harness C, which now has a higher risk of failure. Now, if we say that, okay, as a policy, we want to make sure that nothing is in the area identified in red, well, then the first course of action would be say, okay, let's replace the wire harness. And that's pretty straightforward. We replace the wire harness, we reduce the probability of failure because we've reduced the chance of age-related failures, and the probability of failure has been reduced significantly. But the next step here is that, well, okay, replacing the wire is a nice and easy approach. Replacing the harness is very simple. Well, if we take just a little bit more time and see where are the areas that have why is it a high severity of failure? So let's say in this case, the wire harness was routed near a hydraulic line. And if this wire harness had a failure, well, then there's going to be a flamethrower when that hydraulic line ruptures. So if we can just do a small change, perhaps reroute, add harness protection, whatever, we make a slight change, we reroute the wire, we then reduce the failure severity, and at this point, we've moved the wire harness from a high severity of failure to a slightly lower, and reduce the probability of failure through replacement and harness modification. Task 6 is where you take action, and really for any EWIS program, any sort of life extension, there are 4 actions that can be taken. First, no actions are necessary. The analysis finds that the wire harness is in perfect condition and no further actions are necessary. This would be a great case. This would be wonderful if wire never degraded and EWIS components never had any sort of age degradation. But we know better. We know that these components will degrade over time. And that doesn't mean to say that you won't find an aircraft that needs no actions. We've certainly, through our analysis, found several fleets where they've been in good condition and no additional maintenance no changes have been needed. The next thing that could be done is increase or modify maintenance actions. Certainly this area, the analysis could find some areas where the degradation is very high, and additional maintenance could potentially extend the life of those components, or at least ensure that if there is any degradation, if there's any increase in the number of failures, that they're handled either shortly before or shortly after they actually appear. Next action, a wire harness replacement. Now, this is obviously not ideal for many fleets, but sometimes it's necessary. But as I said earlier, there's never been a case where we've worked on a fleet and we found that all the wiring or EWIS components need to be replaced. We can focus on those areas that have the high degradation, restore the aircraft wire system reliability just by replacing some of those wiring harnesses. And then obviously the last action is a design change. Can we modify the routing, protection, and so forth? And that really comes down to a case-by-case basis. Each of these come down to a case-by-case basis. And from this, we come down to the 3 takeaways here. The EWIS assessment process outlined in Mill Handbook 525 it's a great comprehensive process, and it's customizable to each fleet. But when going through this, identifying the scale of maintenance issues and just focusing solely on the maintenance will not predict future performance. Component performance assessments are necessary to determine remaining reliable service life. And lastly, risk is a combination of probability of failure and the severity of failure. A full EWIS assessment can address both and provide data necessary for planning future maintenance actions. So if that's all you take away from this presentation, from this webinar, I will be a happy man. Like I said, we're going to have this webinar available in a couple weeks. We'll make it available to the participants here first. This is the time where we can start answering some questions. Thank you for your time. Of course, I always will say anytime we have a presentation, I imagine most of the people here saw it either LinkedIn or through our newsletter. If you haven't signed up for our newsletter, lectromec.com/newsletter. Also, if you have any questions about EWIS assessment, degradation evaluation, we have a lot of articles on our website. I think right now we are pushing, we maybe over the 300 mark in terms of number of articles, white papers, and so forth on this topic. Again, I'm Mike Traskos. If you have any questions, my email address is here. Thank you for your time.